There's a planet out there where it rains molten glass sideways at 5,400 miles per hour. And bluntly, that's not the weirdest one. In 11 minutes, I'll explain every type of exoplanet we've found. Quick ground rules. Exoplanet. Any planet orbiting a star that isn't our sun. We've confirmed over 6,000. The real number is probably in the trillions. We spot them two ways. Transit. Planet crosses star, star dims. Radial velocity. Planet tags the star wobbles. From dips and wobbles, we pull mass, size, temperature, sometimes atmosphere. Then we sort them into buckets. Let's start with the type that looks most like home. Terrestrial planets, rocky worlds, iron core, silicate mantle, thin crust, maybe an atmosphere if the star didn't strip it. Earth, Venus, Mars, Mercury, same recipe. Out there, the poster child is Proxima b, orbiting our nearest star. Then TRAPPIST-1, 7 rocky planets stacked around a single red dwarf like a cosmic bowling alley. Three-seat habitable. Habitable zone, the ring around the star where liquid water can exist. Not too hot, not too cold. Goldilocks. Here's the catch. Almost every rocky planet we've found orbits a red dwarf, and red dwarfs are bluntly dim. To stay warm, the planet hugs the star. Hug long enough and tidal forces lock one face forever. Permanent day on one side, permanent night on the other. A thin twilight ribbon where anything interesting might live. Red dwarfs flare constantly. Imagine your sun burping a solar storm at you every few days. That's the neighborhood. Scale one of these rocky worlds up though, and physics essentially starts getting nasty. That's the next bucket. Enter the super-Earths. 1.5 to 2 Earth radii up to 10 Earth masses. Surface gravity? Absolutely brutal. Hold an atmosphere and it's thick, crushing, opaque. Nudge the radius higher and you cross the invisible radius valley. Above it, you're not a rock. You're a mini-Neptune. Small solid core, huge puffy envelope of hydrogen and helium. Here's the thing. Mini-Neptunes and super-Earths together might be the single most common planet type in the galaxy. Wild thing is, we have exactly 0 in our solar system. None. We skipped that size bracket entirely. The most typical Milky Way planet is a category with no local reference, no probe data, no known surface. Assuming there even is a surface. Now go bigger. Because once you scale up, gas giants get exotic fast. Gas giants. Jupiter analogues are the boring ones. Massive, cold, parked in long, lazy orbits far from their stars. Ice giants, the Neptune-likes, sit even further out, packed with volatiles. Water, ammonia, methane frozen under crushing pressure. Fine, predictable. But in 1995, astronomers found 51 Pegasi b orbiting its star in 4 days. 4 days! Half Jupiter's mass closer to its star than Mercury is to ours. It shouldn't exist. Gas giants form in the cold outer disk, where ices clamp. So how did this one migrate inward? Migration. Early on, the disk of gas and dust drags on baby planets and pulls them inward. Some stop halfway, some plunge into the star, some park just above the surface and cook. Hot Jupiters. And bluntly, hot Jupiters are the friendly ones compared to what comes next in this catalog of weird words. Ultra-hot Jupiters. Same idea, cranked to 11. Dayside temperatures north of 3000 Kelvin, hotter than some stars. At those temperatures, molecules literally fall apart. Water doesn't exist. Iron doesn't stay solid. Basically, chemistry breaks. On WASP-76b, iron vapor floats on the scorching day side, then rains as liquid droplets on the cooler side. Yes, it rains iron. And here's where it gets weird. HD 189733b has silicates in its atmosphere. Winds tear across the planet at over 5,000 miles per hour. The silicates condense. They fall as molten glass. Molten glass blown sideways by hurricanes that never stop. That's the planet from the opening line. Essentially hell with weather. Then there are the puffy planets, gas giants so bloated by stellar heat their average density is lower than cork. Drop one in a bathtub the size of a small galaxy and it would float. Basically, cosmic marshmallows. Every one of these hot giants is tidally locked. One phase melting, one phase freezing, winds redistributing the difference. But even weirder, planets made of things planets shouldn't be made of. Ocean worlds, for instance. Not a small sea like Earth's, not even a big one. A global ocean, hundreds of kilometers deep. No continent anywhere. No seabed a submarine could reach. At the bottom, pressure crushes water into exotic ice phases. Ice 7, Ice 10, solid ice hotter than boiling water, held together by pressure alone. Imagine that. Moving on, lava worlds. Rocky planets orbiting so close to their star, the dayside is a permanent magma ocean, sloshing under a sky of vaporized rock that rains back down as pebbles. Basically, weather from hell. Carbon planets form in systems with more carbon than oxygen. The mantle is graphite and deeper, kilometers of diamond. Iron planets. Think Mercury, but bigger and denser. A collision stripped the mantle, leaving a naked iron core wandering. Chthonian planets, the ghosts. Hot Jupiters whose star boiled off their entire atmosphere over billions of years. What's left is the exposed rocky core, still radiating, essentially a gas giant reduced to a corpse. But here's where it gets weird. Some planets shouldn't exist at all. Rogue planets. No star, no orbit, just drifting alone through interstellar space, dark and cold, kicked out of their birth systems by gravitational chaos. There might be more rogues in the galaxy than there are stars. Trillions, invisible unless they pass something bright. Some might hold enough internal heat for a subsurface ocean, life without sunlight, in the dark between stars. Imagine that. Next up, pulsar planets. A pulsar is the corpse of a star that went supernova, now spinning hundreds of times per second, blasting lethal radiation. And yet, planets orbit these things. The very first exoplanets we ever confirmed, back in 1992, were orbiting one of these pulsars. 3 worlds, bathed in lethal radiation, somehow still there. Nobody knows if they survived the supernova blast, or formed later from its ashes. Either way, planets orbiting a dead star's radioactive corpse. Somehow. Circumbinary planets, basically Tatooine. 2 stars, 1 planet orbiting both. Kepler 16b was the first confirmed. Real double sunset. High cyan worlds, hypothetical until recently, now the hot lead hunting life. Deep oceans beneath thick hydrogen atmospheres. Warmer and bigger than Earth, habitable across a much wider zone than rocky worlds ever managed to be. Record holder PSRB 1620b, 12.7 billion years old, almost as old as the universe. It was already ancient when Earth was still cosmic dust. What does this whole zoo mean for finding life? Here's the thing. Earth-like, rocky, right size, right temperature, oxygen atmosphere, liquid surface water, is not the default. It's statistically rare. The galaxy actually prefers super-Earths, mini-Neptunes, hot giants, and drifting rogues wandering between stars. If we only look for copies of Earth, we might miss almost everything out there. So astronomers switch tactics. James Webb now sniffs the atmospheres of transiting planets by splitting the starlight that passes through them. Each molecule leaves a fingerprint: water, methane, carbon dioxide, and, if we're lucky, biosignatures, chemistry impossible without life. K2-18b, a Haitian candidate, showed hints of methane, carbon dioxide, and possibly dimethyl sulfide too. On Earth, dimethyl sulfide is made almost entirely by ocean plankton. The signal is disputed, the debate loud, but it's our first serious scientific argument about life on a specific world beyond the solar system itself. Habitability, turns out, is broader than we assumed. Life doesn't need Earth, just liquid water and time. In the next decade, new telescopes will directly image nearby rocky worlds, actual photons from actual alien surfaces. When that first spectrum comes back carrying oxygen it shouldn't have, everything changes. One last thing before you go. I bluntly explain space every single week. No filler, no fluff. Hit subscribe if that sounds useful to you. Next up, how we'd actually detect alien life if it is really out there.